Hello everyone, I am Himanshu Vasnani from Department of Mechanical Engineering. I am here to discuss on the subject Material Science. The subject code is ME207, unit number 3, lecture number 17 in the series. Today's topic are Austempering, surface hardening of particles, carburizing process and nitriding process. So, our objective is to provide the student with a basic understanding of Austempering, surface hardening of particles, carburizing process, and nitriding process. And today's outcome after this lecture will be students will have learned the basics of Austempering, surface hardening of particles, carburizing process, nitriding process, and students will understood various steps of carburizing process and nitriding process. So let's start with today's lecture. Now we are studying about heat treatment processes in which we studied about annealing process, we studied about normalizing process, we studied about hardening process, we studied about you can say various other processes. So in those during those processes, we are now continuing with the other processes also, like austempering and or isothermal quenching. So the component or the specimen to be hardened is first austenized and then quenched into a lead or salt bath held at just above the Martensite transformation temperature. We've discussed about this Martensite transformation temperature in the previous classes also, that how what is this temperature. So here what it is saying, the component or the workpiece that is to be hardened, it is first austenized, okay, and then immediately it is dipped or quenched into the salt bath or lead bath, which is held just above the martensite transformation temperature. So the quenching means that to cool down the temperature and release the heat. Okay. So the component is kept into a bath until the bainite transformation is completed. So our purpose behind all these things is to complete the bainite transformation process in this specimen. Now the component is removed from the bath and cooled in air till the room temperature is reached. Okay. So the bainite so produced is somewhat softer than martensite of the same carbon content and distortion is also minimum. So in this way you get a better workpiece, okay, of the a better you can say better you can say bainite, okay, which is somewhere it is had somewhere a softer than martensite, okay, having the same carbon content and the distortion inside is also very minimal. So you get a better bainite structure. Now, in this, the Austempered steel has improved shock resistance. Okay, now the shock resistance is also increased and low notch sensitivity is there. Now you can see in this figure on the right hand side, it shows the Austempering on the triple T curve. On the horizontal axis, you have the time log. Okay, the time is there on the horizontal axis. Okay, and on the vertical axis, you have the temperature. So you can see how this the whole graph is coming, or the center is going, and what about the source is there. Okay, so in this way, this kind of curve we have also discussed this curve in our previous classes also. Okay, showing the process of Austempering. Now, certain molten salts or is having 45% NaNO3 and 55% KNO3, or molten alkali is having 20% NOH or 80% KOH. These are used as quenching medium in this isothermal quenching, and their temperature is maintained between 150 to 450 degrees centigrade. Okay, in this process, we use various these molten salts that they have discussed with us, like 45% NaNO3 or and KNO, 55% KNO3, or molten alkalis of having 20% NaOH or 80% KOH. They all are used as quenching medium in this. Okay, and they have a certain temperature which they maintain. Now, tempering is a heat treatment and no retreating is required as in tempering. Okay. So it is an advanced level of heat treatment, tempering. Okay. And after this tempering, you do not require again a retreating. Okay, reheating, sorry. Now, tempering is often limited to sections thickness of 20 mm. Okay. Now, this is only a limitation in tempering. That is, only small sections are suitable for tempering, as big sections cannot be cooled rapidly to avoid formation of perlite. Okay, so we have this limitation in Austempering. Okay, because big sections you cannot cool them instantly. Okay, and avoid the formation of perlite. We want those components, those sections which can be cooled. Okay, fast. So the Austempering process is done in those parts which have a thickness of around 20 mm. Okay. Now, Austempering is capable of to a few plain carbon steels. Okay, and requires facility of molten bar. Okay, the molten bath that we have discussed in the previous slide, the composition that we discussed. Okay, now if the after the Austempering we require that salt bath. With the help of those that salt bath, you can process the Austempering process. Okay, so this Austempering process is applicable to a few carbon steels, and that molten bath is required in it. One may regard it as a disadvantage over quenching and tempering. But you know, there are some processes, there are some materials which require a particular application, and to perform that particular application, we require certain properties. So, austempering is a process to attain those properties which are required in that particular operation or in a particular application. Okay, so irrespective of every disadvantage, we can also go with this process also depending upon the application. Okay. Now, martempering and steeped quenching. That was austempering. That is now it is martempering. Now the sample here, okay, the sample or the specimen to be hardened is fully austenized again, okay, and then quenched into a lead or salt bath held at a temperature just above at that martensite start to form. Okay, understand the difference between austempering and martempering. Here also, it is heat hardened. The sample is or the specimen is to be hardened as fully austenized. Okay, it has gone to that much extent, and then caused into a lead or salt bath. Okay, held at a temperature just above at which the martensite begins to form. Okay, now it is maintained at this temperature until the temperature becomes uniform throughout. There is no difference in inside and outside temperature. Okay, the uniformity is of temperature is throughout the structure or inside and outside both. Okay, then it is water quenched to form complete martensite structure and bayonet formation is prevented. In previous what it was then quenched and then allowed to cool in air. Here it is water quenched. Okay, now this is the difference between both austempering and martempering. Then it is water quenched to form complete martensite structure and then bayonet formation is prevented. It is more focused to martensite structure. Okay, you can see on the right hand side the diagram is shown to you of between time and temperature and how this curve is gone. Now this process separates successfully the cooling contraction from the uh, austenite martensite expansion and thus prevents quenching in large size articles. This process, okay, this has its own features. Now the steel can be tempered to low temperature to further refine the structure. Okay, it has its application. Okay, each of such treatment is to minimize cracking. Now, whatever we are doing, it will have some applications. Okay, we are not doing anything just for you can say fun. We have application, so we require some properties. So here, by this martempering process or steeped quenching process, this says that effect of such treatment is to minimize cracking, distortion, and the thermal shock of the quenching. Okay, the hardness and the ductility are usually similar to those obtained by direct quenching to the martensite state, followed by tempering. However, the impact toughness may be better. So they have given that that this steel can be tempered to low temperature to further refine the structure. So here you can say that this steeped quenching or martempering this had its application. Okay, with the help of these treatments that we are doing, we can minimize cracking or distortion and the thermal shock of the quenching. So this is okay. Good. Now surface hardening. Now this is also a kind of a heat treatment process like we did earlier. After tempering, we are studying about you can say surface hardening. Okay, this is also a kind of heat treatment process. Now, surface hardening of articles, like most of the surface strengthening, chemical retreatment, chain hardening, or knurling, etc., what offers an additional advantage that large compressive stresses appear in the surface layers of hardened articles. They gave this advantage. Okay, in surface hardening, what they gave an advantage that the large compressive stresses they appear on the surface layers of hardened particles. So this is something good. A number of components, okay, they require only a hard surface to resist wear and tear and a tough core to resist shock loads instead of complete component made being made hard. Okay, so these two properties do not exist in one steel. Okay, they some of depending upon the application. Okay, we may require some components, okay, that require a hard surface on the upper side. Why we require the hard surface? So that wearing and tearing can be resisted or avoided. Okay, and a tough coat to resist shock, okay, loads instead of the complete component made being hard. Okay, so we know that only if the surface is hard or the core is tough, these two properties they do not exist in one common steel or in one steel. Okay, so for toughness, one finds that the core should not exceed 0.3% carbon content. Now we are talking about the experimental data. Okay, they say that for toughness, one finds that the core should not exceed 0.3% carbon content. Okay, 0.3% carbon content, and also sometimes it is not desirable. It is not desirable to harden complete component. For example, it is undesirable to have case hardening through the screw threads. So we don't require them. The threads would be brittle and distortion during hardness would need expensive thread grinding operations to correct the distortions. Okay. Now this is they have in the past experience faced such kind of issues that we cannot go for case hardening of the screw threads. Why? Because the threads that are there in the screw they may be brittle and distortion during hardening, and to again you can say again regain the you can say threads again it would need expensive thread grinding operations because due to distortion it may get disturbed. So to correct those unwanted distortions we need to go some other process it may be expensive. Okay, so surface hardening is classified into two types. The first is selective heating of the surface layer. See, uh, whatever heat treatment processes they are you can say we are studying. Okay, they are as a result because of the past experiences. They have tested it, they have finded the conclusion, and now they are saying that in these particles, you can say you can go with these processes, which will be successful. Okay, engineering is all about making the things easier, and material science engineering is all about making the materials better for machining, better for manufacturing, and better for machining. So that is why we are studying about this process of heat treatment. So now we going with the first type, selective heating of the surface layers. Now in this case, the time available to change the microstructure of steel is short. Okay, so obviously hardened and tempered steels. What? Hardened and tempered steels they respond well, but annealed steels do not. I repeat. See, in this, what we are saying that the hardened and the tempered steels they respond well when we are going to change the microstructure. But annealed steels, okay, they do not respond in a well way because in terms of annealed steels we cool down the you can say whole material in the furnace only, so it takes time. So moreover, composition of the steel must be such that the quenching will produce martensite and so harden the steel. Okay, we have to choose the composition along that only. Now, clearly carbon content to be 0.4% or more. Okay, so the flame hardening can be done, be one of the methods of selective heating. So if we go for the selective heating of surface layers, then we can go with the flame hardening. Okay, with the process. Now, surface of a component is heated to 850 degrees centigrade. Okay, now we're going with the flame hardening. Okay, now the surface of the component is heated to 850 degrees centigrade with an oxyacetylene flame and quenched with cold water immediately. Now this is a process, okay, where you are heating the workpiece to this temperature, 50 centigrade, with a flame that is oxyacetylene, okay, that we see in the gas welding, and then quenched with cold water immediately. Okay, now flame heating this transforms the structure of the surface layer to austenite and quenching. Okay, and quenching like with cold water they say. Quenching changes the austenite surface layers to martensite, resulting into a hard surface. Okay, now our motive is to obtain a hard surface. So what they say, they simple heated the surface or heated the material with a flame and changed its structure to austenite and then immediately quenched with cold water. Okay, and changed the austenite surface layers to martensite. And with the changing from austenite to martensite, what they say, it resulted into a hard surface. This resulted into a hard surface. Now, depth of hardening depends on the heat supplied per unit time. You can see what is how the flame is helping and the hard surface is obtained. Now, flame hardening is mostly used in case of carbon and alloy steels having carbon content of 0.64 or 0.4% to 0.6%. Okay, this process of flame hardening of of getting a hard surface, it is mostly used in case of materials having carbon in the range of a carbon content of 0.4% to 0.6%. And they have given the examples also like shafts or gears or cylinder liners or crankshafts or general bearings. So it depends. Okay. Okay. Another method of selective heating is induction hardening. Now they are going with another process that is called as induction hardening. See, the style of you can say understanding the procedure should also be there. So now induction hardening. The steel components they are placed within a coil. Okay, through which a high frequency is allowed to pass. Now the surface layers of the component are heated between 850 degrees centigrade to 1000 degrees centigrade. It depends from, it ranges from material to material, but we can say that uh, when the surface layers of this components that we are using with the induction hardening, they are heated to about 850 degrees centigrade to 1000 degrees centigrade. Okay. Now subsequently cooling transforms the austenite to martensite. Then the purpose is that the heating coil is often made of tube perforated with fine spray holes that it can be used for heating and quenching also. Okay, it can be used for heating and quenching also. So the depth of heating produced by this method is related to the frequency of the alternating current. Okay, the frequency of the AC. Okay, it is also having its importance. Like how much the depth of heating will be there. Now, higher the frequency, okay, higher the frequency of AC current, the less will be the hardened depth. But there will be a more rapid rise in temperature. If you increase the frequency of the AC current, then there will be less hardening. But in terms of temperature, there will be rise in temperature, a rapid rise in the temperature. Okay, you can see the parameters that they are telling you are in this process. Okay, now the case hardening. Now, okay, we are done with the induction hardening, and then we are going to do case hardening. Now, this is also a very important thing. Okay, what happened that in this method, like carbon or N2 are introduced in the surface layer. Okay, so in carburizing, when the part is surrounded by material or atmosphere rich in carbon. In carburizing, what we do, the part that we are working on it, the workpiece, if it is surrounded by material or atmosphere rich in carbon, and on heating, this carbon is first released and then absorbed in steel. Okay, that is the you can say go for carburizing. Now, more recently, the case carburizing is more effective performed by heating steel part in the atmosphere of natural gas, coke, even gas, butane or propane or volatilized form of liquid carbon. It's like you can say terpness and benzene or the volatile form of liquid hydrocarbons like tempness and benzene. Volatile form of carbon and glycols or ketones have been also used. You can see that how this carburizing, how it is more effective. Okay, but we also need to find some other process also. Okay, now in these cases the thickness of the hardened layer is proportional. The layer which is thickened is proportional to the root of the time of treatment in hour. Okay, it is proportional to the root of the time of treatment in hour. Now the depth of hardness, the layer, okay, the depth of hardness depends upon the number of times the process is repeated. Okay, it depends upon the number of times the process is repeated. So the component is finally raised to a red heat, okay, and quenched in water. Okay. However, one will have to take precaution that the part to be hardened should be covered with the compound. You have another, you can say, precaution to be there. Okay. Now we go with the carburizing process. See, every process like case hardening, like tempering, they all are important, but their application is dependent upon the material and the conditions in which we are. So now carburizing process. Carburizing process is an also another heat treatment process. Okay. Okay, then it is also you can say one this method should be done in a controlled manner. Okay, not just going with the flow. This should be done in a controlled manner. So let's start with carburizing. There is another method of surface hardening. So the composition of surface layers are changed. Okay, the composition of surface layers are changed. In previously, what we were doing hardening of surface layers, or we are trying to release the internal stresses available in the workpiece, or maybe due to metalworking process, or maybe due to the casting or welding process. But here now carburizing here that is under matter of surface hardening and maybe the composition of surface layers are changed. Now the process is simply carried out on a steel containing less than 0.2% carbon. Okay, it is carried on a steel containing less than 0.2% carbon. So carburizing is usually employed for treating certain types of machine elements which have to have a wear resistance working surface. This is only you can say employed for those machine elements which have a wear resistance working surface. And secondly, a tough core. Okay, like gear wheels and shafts and pins, shafts, worms. So the initial medium for carburizing, the initial you can say medium for carburizing like carbon saturation is usually called a carburizing. Okay, so you can see in the diagram on the right hand side also how this, you can say, heat treatment work is done, how the temperature is raised so high to attain particular states of, you can say, structure. Now for carburizing, two methods of carburizing are in use, like in a solid or in a gaseous carburizer. Okay, so we have to be careful while studying these. So in both cases, however, the carburizing process, okay, it possesses a gaseous phase. The most popular solid carburizer consists of a charcoal with an addition of 20-25% barium carbonate to intensify the process, and 3 to 5% of CaCO3 to prevent the carburizer particles from caking. Now see the precautions and the caring required for carburizing process. Okay, you can say that the most popular third carburizer consists of a charcoal for carbon with an addition of this much 25% barium carbonate. Okay, and to intensify the process, and then 3 to 5% of CaCO3 to prevent the carburizer particles, okay, from kicking. Kicking means bundles of this powder, this carburizer particle. Now, articles to be carburized and the carburization are forced, you can see, also placed in a container, steel box, and heated in a furnace to this much temperature, 910 to 930 degrees centigrade. So during heating, the charcoal reacts with the oxygen of the remaining air. Okay, now this is the, you can say, equations like coming. Okay, let's get to the there first only. That in this, what happens? The articles that we are taking, that we are carburizing. Okay, so what we do, they are first placed in a container. Okay, now the container should be of steel if possible. Okay, and then they heated this material and in the container to the furnace at the temperature of, you can say, 910 to 950 degrees centigrade. So during this heating, the charcoal that we are using, okay, it reacts with the oxygen of the remaining air, like C2C plus O2 goes 2CO, or you can say BaCO3 C is BeO plus 2C. The leading reaction of carburizing takes place in the surface of metal of is the disproportioning reaction. Okay, you can say that 2CO gives CO2 plus C. The active carbon that forms by the reaction is absorbed in the surface of the metal. The surface absorbs the carbon, okay, which is the austenitic state, while CO2 reacts with charcoal to form new portions of CO. So you can see in the upper first or the first reaction 2C plus O2 means 2CO. So how this, you can say, CO2 is reacting with charcoal, okay, to form new portions of CO. Now the carbon content formed in the reversible disproportioning reaction is transferred to the into a surface being saturated. Okay, so here how we just process this. This Okay, and now we are doing this. Now is gas carburizing, the carburizer is diluted natural gas. Okay, the carburizer, what is this? It is in gas carburizing. Okay, in gas carburizing, what we do, the carburizer which we are using, it is a diluted natural gas. Okay, it's consisting of almost full of methane, maybe methane is there, and a controlled atmosphere produced in special gas producer and a liquid hydrogen, like for kerosene, benzene, etc., supplied drop-wise into an airtight furnace where it forms an active gaseous medium. Okay, what we do in this gas carburizing, we use natural gas, maybe methane, in a controlled atmosphere. Okay, we need atmosphere and a liquid hydrogen, maybe of kerosene or benzene. Okay, All these things it is supplied dropwise into an airtight furnace where it forms an active gaseous medium. So the leading reaction for methane is like CH4 gives 2H2 plus C. So in some cases when the gas mixture contains CO and endothermic base controlled atmosphere, the reaction to CO gives CO2 plus C is also possible. Okay. Now depending on the composition of gaseous mixture, depending on this composition of gaseous mixture and the concentration of carbon in steel, the atmosphere in the furnace may be carburizing, decarburizing, or neutral. Now, here it needs to be clear. Depending on the composition of gaseous mixture, okay, the concentration of carbon in steam, the atmosphere in the furnace, it may be of three types like carburizing or decarburizing or neutral. So when carburizing will take place, when the carbon concentration in the surface of steel is smaller than the carbon potential of gaseous mixture at the given temperature. When it will happen? When the carbon concentration in the surface of the steel that we are using is smaller than the carbon potential of gaseous mixture at the given temperature. Normally, this process that we are doing is carried out on a steel containing less than 0.2% carbon. This process that we are doing is normally done when we have steel which is having 0.2% less than 0.2% carbon. So to achieve adequate hardness, the surface of the component should have a carbon content of 1% approximately. Okay, so in this process, the carbon is usually added to the surface layers up to zero point 0.7 to 0.8% by a carefully regulated depth, which is followed by a quenching process to convert the surface layers into martensite. Okay, to achieve such kind of hardness, the surface of the component it should have a content of carbon content of 1%. Okay, so in this process, the carbon is usually added to surface layers up to 0.7 to 0.8% by carefully regulated depth. Okay, you can show how they are balancing it, which is followed by a quenching process to convert the surface layers into martensite. Okay, so in this way they go for the whole process of this. Now this process is carried out on a steel containing less than 0.2% carbon, and they in this way did this. So the structure obtained or carburizing is coarse grain since the metal is held for an appreciably long time at the carburizing temperature. The time of isothermal holding in carburizing depends on the grade of steel and the desired depth of flow. Okay, now the parameters are coming. This a time of isothermal holding in carburizing it depends upon the grade of steel obviously and the desired depth of flow. Okay, the process of gas carburizing occurs more quickly than that of solid carburizing since no time is lost for heating the carburizing process. Okay, when you talk about solid carburizing and gas carburizing, so we can say that the gas carburizing is more quick than solid carburizing. Okay, because there is no time is lost for heating the carburizing, and also the gas carburizing can be more easily controlled and automatized. By carburizing process, hardness can be increased from 200 HP for 0.8% carbon content in the core to 750 HP for having 0.7% carbon content in the surface. So you can see the variations of, you can say, increasing the hardness through carburizing process. To understand the carburizing process, the importance of carburizing heat treatment process. Okay, how it's helping. Another methods for carburizing are like pack carburizing. Means the component to be carburized is heated above a temperature between 850 degrees centigrade to 1060 degrees centigrade for about 5 hours in a sealed metal box containing charcoal and barium carbonate. Okay. Now oxygen present in the box it reacts with the carbon to produce carbon monoxide. So carbon content in the atmosphere gets diffused into the surface austenitic layers of the components. When carburizing is complete, the metal boxes are allowed to cool down so that they can open and unpack. The components are then cleaned and made available for subsequent heat treatment. So where you have the large components or where you want a thick surface layer to be hardened, you go with the back carburizing process. Okay, they have this facility of hardening the you can say large components or where you want the thick surface layer to be hardened. Okay, so this kind of process is applicable to that. Then salt bath carburizing. Now this method, okay, this involves the component in a bath of suitable carbon-rich salt between the 750 degree to 850 degree centigrade. Usually sodium cyanide is mainly used as a medium, and you can say the carbon from this salt, from this molten salt, okay, it diffuses into the component. The purpose is hardening. Now, the advantage and disadvantage of this cyanide salt that we are saying. The sand salt is poisonous in nature, so obviously one will have to take utmost care while working with such a salt. A few grains of this salt under the fingernails would prove fatal if transformed to mouth via soap or smoking or food. So after this treatment, when this sodium cyanide is used and carbon from this molten salt is diffused into the component, after this treatment, the removal of the salt from the hardened surface is more problematic in case of blind holes or threaded parts. So this process, heating and carburization are more uniform with less chances of distortion. The components can be hardened by quenching straight out of cyanide salts without need for further heat treatment. Okay, it can be further hardened by quenching straight out of cyanide salts without the need for further heat treatment. Now nitriding. See, nitriding is also a very good heat treatment process. Okay, normally we have some parts like worm gears or shafts or various machine engine components like cylinder sleeves or crankshaft. They use nitriding technique. So what we will do is the process of diffusion saturation of steel surface with nitrogen. Okay, we are using now. You are taking the help of nitrogen. The component is heated in a mixture of ammonia and hydrogen so that nitrogen diffuses into the surface layer and hard nitrate compounds are formed. The process is employed for increasing the wear resistance and endurance limit of machine elements like crankshaft or cylinder sleeves or worm gears or shafts. So prior to nitrating, steel articles are subjected to hardening and high temperature tempering, which improves heat treatment and finishing. And after nitrating, they are ground and polished. You can see why we are doing this. We are trying to improve the wear resistance. We are trying to improve the endurance limit of machine elements. And how we are doing this? We are you can say trying to diffuse the nitrogen into the surface layers. Okay, and form the hard nitride compounds. Okay, and how we are doing this? Then we are trying to heat the component in a mixture of ammonia and hydrogen, and we are trying to diffuse this nitrogen into the surface layers. Okay, so you can understand the variety of heat treatment in the you can say engineering industries, or in the engineering you can say. So you can see in the figure on the side, you can see the commonly nitrate parts that I've shown you in this one. So the nitrating process, the component is heated in a mixture of ammonia and hard nitride compounds are formed. So common nitrating is carried out at a temperature of 500 to 600 degrees centigrade. Okay, in a muffle or container through which the disassociating ammonia is being passed. So This process is used with those alloys of steel which contain elements that form stable nitride, example chromium, molybdenum, tungsten, vanadium, aluminium. So these are, you can say, the elements. Okay, they form stable nitrides. So we can process such nitriding process with these kinds of you can say alloys or elements. It is probable that the reaction of ammonia dissociation takes place at the steel surface. Nitrogen ions are absorbed by the surface and then diffuse into the depth of the steel. The time taken for nitrogen to react with the steel surface is about 100 hours. Okay, they're given the reaction like 2NH3 gives N2 plus 3H2. Okay, this is possible. And the molecular nitrogen formed by this reaction that I just told you, the nitrogen formed by this reaction which cannot diffuse into the metal being ionized. The depth to which the nitrides are formed depend on the temperature and time allowed for the reaction. Okay, the depth to which the nitrides that you are using are formed depend on the temperature and the time allowed for this reaction, and the normal conditions unlikely to exceed 0.7 mm. The depth which we are talking about, okay, to which this nitrides are formed, it, it depends on the time and temperature that you are allowed for this reaction. Okay, now here the temperature and time are important. So time and temperature allowed for this reaction. And the normal condition is unlikely to exceed 0.7 mm. The components are cooled slowly in the ammonia hydrogen atmosphere, and the process of nitrating is usually completed with the formation in the metal surface of the phase with an HCP lattice and order and management of atoms in the wide range of concentration. Okay. Now, when nitrating carbon steel, the rate of nitrogen diffusion decreases with an increase of carbon content, and the formation of carbon nitride phase becomes possible. So you can, how it is seen, a thin white layer of nitride is formed on the surface of the component, which should be removed by mechanical or chemical means, as this layer adversely affects the mechanical properties. Okay, this whole process you can find out that a thin white layer of nitrogen is formed on the surface of the component. Okay, which is formed by which is should be removed by mechanical or chemical means and this layer adversely affects the mechanical properties. So you can say that when we discuss that this process takes about 100 hours, so we can say that this process is the time consuming process. Okay, so nitride layers of alloyed steels have higher values of hardness and wear resistance compared with carburized layers. So here no quenching is required for with night riding or cracking and distortions are less likely to occur. So apart from this, let's start with our you can say process of MCQs. So in Austempering or isothermal quenching, the component or specimens to be hardened is called austenized and then quenched into a lead or salt bath held at just above the martensite transformation temperature. So what do we call? So is it true or false? It is true. It is true. Okay. Interestingly, Austempering is a heat treatment and no reheating is required as in tempering. We just discussed at the starting of the lecture. It is true. Now in Austempering, molten salts such as like 45% of NaNO3 and 55% KNO3 or molten alkalis of 20% NaOH, 80% KOH are used as a quenching medium. So what do we call this? True or false? It's true. Now Austempering is often limited to a section thickness of 13 mm, okay, in millimeters. This is only limitation in Austempering because that is only small sections are suitable for Austempering as big sections cannot be pulled rapidly to avoid formation of pearlite. So what is the thickness that has the limitation of Austempering? It is 20 mm. Okay. It is in this 20 millimeters. 20 millimeters. Now, carburizing is usually employed for creating certain types of machine elements which have to have a wear resistance working surface and tough core, like gear wheels or shafts, pins, camshafts, cam movements, etc. Is true or false? It is true. The initial medium for carburizing like carbon saturation is usually called the carburizing. Is true or false? It is true. Now this is the process of diffusion saturation of steel surface with nitrogen. We just read a few slides before. What do we call this? Diffusion saturation of steel surface with nitrogen, called as nitriding. Now in this process, the component is heated in a mixture of ammonia and hydrogen, so that nitrogen diffuses into the surface where then hard nitrate compounds are formed. What do we call this? We call this as nitriding. Now this process is employed for increasing the wear resistance and endurance limit of machine elements. That is the crank shafts, cylinder sleeves, worm, gears, shaft, etc. What do we call this process? Okay, we call this as nitriding. Now, the last question for today. Nitriding is carried out at a temperature of this much temperature in a muffle or container through which the dissociating carbon is being passed. So, what is the temperature of carrying out this nitriding process, which usually is 500 to 700 degrees centigrade? This temperature is around 500 to 700 degrees centigrade. So, at this temperature, the answer is B. You can have the process of nitriding. So, we try to discuss as much as possible for a particular process. And this process obviously is important in terms of, you can say, heat treatment, because heat treatment is all about making the material better for the application. So if you know the application, you can do the required amount of heat treatment all by yourself. These are the references which you can refer for further study. So this is all for now. Thank you.